Thank you very much for the invitation. It's an honor for me to participate at this Congress. My presentation is about hydrodynamic resistance in Finswimming. But first, please allow me to introduce myself. My name is Vassilios Gourgoulis, and I am professor in the Department of Physical Education and Sports Science at the Demokritos University of Thrace, in Greece. Let's start. When a body, like a swimmer, like a fin swimmer, is immersed into the water, the force of gravity acts on it. This force pulls the swimmer's body downward, towards the bottom of the pool. Fortunately, the force of buoyancy pushes the swimmer upwards, against the force of gravity, and helps him float. If the swimmer moves his limbs, propulsive forces are generated. In monofin swimming, propulsion is based on the undulation of the swimmer's body. These propulsive forces act to move the body forward. Propulsive forces are the result of momentum flow between swimmer and water, which generates wake vortices. Visualizing the wake generated by a fin, it is observed a clear image of a vortex street. This wake trail consists of paired vortices with opposite sign rotation and a momentum jet between each vortex pair. Unfortunately, due to the density of the water, the swimmer also experiences resistive forces. These resistive forces hinder the swimmer's forward motion. To swim faster, the swimmers should either generate higher propulsive forces or should reduce the resistive forces. Throughout the history of swimming research, different attempts have been made to measure these resistive forces, which are expressed with the term hydrodynamic resistance. Hydrodynamic resistance may be divided in two categories: the passive and the active resistance. The passive resistance, or passive drag, is that experienced by a swimmer's body when performing gliding or during passive towing without movements. The active resistance, or active drag, is that experienced by a swimmer during actual swimming. Active drag takes into account the movement of all limbs during the stroke. The magnitude of the passive hydrodynamic resistance, the magnitude of the passive drag, may be established experimentally by towing a swimmer in a towing tank or exposing the swimmer to water flow in a swimming flume. However, swimmers experience passive drag only during the glide after the start and turns, while fin swimmers start their undulation immediately after the start and turns. Thus, active drag seems to be more important. However, the estimation of the active drag is much more difficult. An approach to estimate the active drag is the use of a specific device called Measure Active Drag System, MAD system. The MAD system allows the swimmer to push off from fixed pads with each stroke, and the push-off forces, the propulsive forces, for each stroke are measured by a force transducer. During this approach, the swimmer must swim with constant swimming speed. Under this assumption that a constant swimming speed is maintained, the mean propulsive force must be equal with the mean resistive force. Consequently, an indirect evaluation of the active drag is possible. However, the use of the MAD system is suitable only for the estimation of the active drag during front crawl swimming and using only the arms. Even though it has been provided a large knowledge on front crawl, it is not suitable for fin swimming. Another method to estimate active drag has been introduced by Kolmogorov and D.P.E.S.S. This approach is called velocity perturbation method. In this method, specific equipment is used, a hydrodynamic body. This hydrodynamic body is attached to the swimmer in order to create a known additional resistance. The swimmer should perform 2 trials with maximal speed. One trial is performed pulling the hydrodynamic body, and the other trial is performed without the hydrodynamic body. Then, the maximal speed when swimming with the hydrodynamic body is compared with the maximal free swimming speed. This approach is based on the assumption that the swimmer is capable of delivering a maximal and constant useful mechanical power output to overcome the water resistance in both conditions, with and without the hydrodynamic body. Hence, the power output during swimming without the hydrodynamic body is equal to the power output delivered during swimming with the hydrodynamic body. Under this assumption, the observed difference in speed should be due to the effect of the known added resistance, and it becomes possible to evaluate active drag during free swimming using this equation, where AD hydrodynamic body is the known added resistance due to the hydrodynamic body, V without corresponds to the speed of the swimmer without the added load, without the added resistance, and V with represents the speed of the swimmer with the added load, with the added resistance. The active drag values obtained using the velocity perturbation method have been compared with the values obtained using the MATS system, and similar results were found, providing that the equal power output assumption in the velocity perturbation method is not violated. However, the use of the velocity perturbation method with a hydrodynamic body generates some uncertainties. The main problem lies in the use of the hydrodynamic body at the free surface while the swimmer is immersed. The hydrodynamic body may oscillate under the free surface and then involve inaccuracies in drag measurement, particularly in wave component. For example, a more pronounced wave formation could lead to more than a quadratic increase of drag with speed, as we will see later. To overcome this limitation, an approach in which the load is controlled outside of the water is preferable. This can be achieved with another approach, the so-called active drag evaluation system. In this approach, which is based also on the velocity perturbation method, the swimmer is linked via a non-elastic wire to a device on the side of the pool. During his or her performance, the swimmer unrolls a spool placed in the device, and the spool's rotation can be braked by adjusting a button that applies on the swimmer a specific load. The force developed by the swimmer to unroll the spool is measured by a torque sensor, and for instance, at speeds close to 3 meters per second, the adjusted load is approximately 20 newtons. Active drag is then obtained using the same equation as in the velocity perturbation method. As you can see in this graph, the maximal velocity with the added load, with the added resistance, the blue curve, is lower than during the free trial, the red curve, and the peak horizontal velocity generally occurs when the fin tail moves downward. The hydrodynamic resistance experienced by a swimmer can be divided into three components: the friction drag, the pressure drag, and the wave drag. Friction is originated in boundary layers. During swimming, a thin layer of water, a boundary layer, which is in contact with the body surface, sticks on it and travels with the same speed as the swimmer. Due to water viscosity, this layer interacts with the adjoining external layer and drags it along with it. The boundary layer closest to the skin is pulled along nearly at the speed of the surface itself, while the layer furthest away is hardly in motion. The magnitude of friction drag depends on the wetted surface area of the body and the flow conditions within the boundary layer. When the water glides smoothly over the swimmer's surface, when the flow is laminar, the friction drag is small. On the contrary, an increased formation of eddies in the boundary layer is accompanied by increased resistance. To form eddies, the water molecules take kinetic energy away from the swimmer. It has been found that swimmers who shaved their skin before a race demonstrated relatively less energy expenditure, greater distance per stroke, and faster swimming speed than those who swam without shaving. Such increased performance may be the result of reduction of skin friction. Thus, the smoothness of the body surface, the hair, the tightness and the nature of the material of the swimsuit and the swim cap are main contributors to friction resistance. However, the relationship of the frictional drag to velocity is linear, causing a minor effect upon performance as speed is increased. The second component of the hydrodynamic resistance, the pressure drag, is the result of hydrodynamic processes occurring at the front and rear of a swimmer's body and is caused by boundary layer separation. When swimming, the water layers are deflected around the body. The boundary layers of the water follow the contour of the body until the flow is separated from the body's surface. At this point, the flow reverses and the separated water layers roll up into eddies, into vortices, which are rotating water masses with high velocity. This flow reverse and roll up into eddies, into vortices, is also observed behind a fin swimmer's body. Due to this water layer separation, the water pressure in the wake of the body is less than the pressure acting on the front. Consequently, a pressure difference created between the swimmer's leading surface in front and the rear of the swimmer. The pressure drag is proportional to the cross-sectional area of the swimmer. Since the monofin swimming motion is undulatory, the cross-sectional area of the body, the projected frontal surface area, S, changes during the stroke cycle, as you can see in these two key events. In underwater fin swimming, the vertical amplitude of the trailing edge is higher than in surface displacement, and this leads to a larger cross-sectional area, inducing more pressure drag. The smaller vertical amplitude for surface swimming points out that the surface of the water reduces the freedom of motion at the ankle joint. To reduce cross-sectional area and therefore pressure drag, a good streamlining is advised, which involves minimizing excessive vertical movements. Pressure drag is also affected by the shape of the body, which is represented by a dimensionless drag coefficient C. A streamlined shape of the body is of decisive importance. Here you can see the flow of smoke around an object with a cubic shape. When the flow reaches the flat front surface of the object, the streams separate from each other and are displaced up, down, and sideward. At the rear side of the object, the streams attempt to fill in behind to re-establish their laminar arrangement. However, because the trailing edge of the object is not tapered, this is not possible, and eddies are created behind the object. In this region, which is referred as the wake, the pressure of the flow is considerably lower than in front of the object, and this pressure difference causes the pressure drag. Rounding the edges that face the flow using a hemispherical object, the disruption of the streams is less, and the wake is smaller. And if we use an object with tapered trailing edge, which is a good streamlined shape, the region of eddies behind the object is reduced and the pressure drag is even less. Here, the leading edge of the object pushes the streams around it in a gradual manner so that they experience minimal disruption, and its trailing edge permits the streams to return to their original position almost immediately after they pass through. The wake is smaller, causing less pressure drag. Thus, adopting a well-streamlined body position, the boundary layers pass smoothly over the swimmer's surface, very little eddy formation occurs, and the pressure drag is decreased. Even if only the head of the swimmer is kept aligned, the drag is reduced. On the contrary, deviations of the swimmer's head from a horizontal alignment cause an increase in the formation of eddies and pressure drag and should be avoided. The maintenance of a hydrodynamic streamlined body position is of decisive importance. Even a slight bend in the elbow, as in the left image, increases unnecessarily the pressure resistance, while the extended arms could reduce the pressure above and in front of the head, thereby reducing the amplitude of the bow wave in a similar manner to the function of the cone-shaped nose below the water line in large ships. As it is already mentioned, the factors affecting the magnitude of pressure drag during swimming at the same speed are the frontal cross-sectional area of the swimmer's body and the shape of the body. However, pressure drag increases with the square of the swimming speed, and consequently, its importance in competitive fin swimming is greater than friction drag, which increases linearly with swimming speed. For swimming near the water's surface, a third component of the total resistance is due to the wave drag. Wave-making resistance is produced when a swimmer moves on the surface or at a small depth under the surface. The mechanism behind this component is a transfer from kinetic energy of the swimmer to potential energy in the formation of waves. With increasing speed, both the wavelength and the wave amplitude increase. Fin swimming trials, as we know, can be divided into two main categories. The first is the displacement at the water surface, and the second is the displacement underwater, using two kinds of techniques, apnea and immersion with air bottles. The world records for both categories show that the mean speed is faster for underwater swimming than for surface swimming. The mean difference of the mean speed is about 7.5% faster for underwater swimming than for surface swimming. Despite the narrower vertical amplitude of the fin during surface monofin swimming and the smaller cross-sectional area, the active drag is greater in comparison with the underwater monofin swimming. And the question arises is, which is the advantage of underwater swimming? The lower active drag during underwater fin swimming by 7% could be attributed to the lower wave drag component. As you can see, during surface monofin swimming there are many waves, in contrast to the underwater swimming. These waves take energy away from the swimmer and increase drag. For the formation of the waves and the magnitude of the wave drag, the depth of swimming is crucial. Although the optimal depth for a reduced drag remains difficult to evaluate, it is clear the advantage of swimming underwater. Maximum drag occurs just below the surface and reaches a minimum at approximately 3 body diameters below the surface. Thus, even in surface fin swimming, the swimmers could reduce total drag if they swim below the water surface for maximal 15 meters after start and turns according to the rules. However, a compromise must be found between the depth of swimming and the time required to achieve it and to return to the surface. With increasing speed, both the wavelength and the wave amplitude increase. Wave drag depends mainly on the swimmer's body shape, the movements in proximity to the water surface, and increases according to the cube of the swimming speed. This means that if the swimming speed doubles, the wave drag increases 8 times. Summarizing, the contribution of each drag component to total drag depends on swimming speed. As friction drag increases linearly with swimming speed, pressure drag increases with the square of the speed, and wave drag is proportional to the cube of the swimming speed, at high swimming speeds in surface fin swimming, the contribution of wave drag becomes more significant. The most common strategy to avoid the influence of wave-making resistance is to swim below the water surface. During underwater fin swimming, the most important drag component is the pressure drag, which is reduced adopting a well-streamlined body position. Thank you very much for your attention. Thank you.